So in last class, we were discussing about the crystal, and I told you the crystal is combination of lattice plus basis. Okay, so your crystal is basically what? Okay, lattice plus basis. Okay, and I told you that lattice again can be classified in two ways. There are some called brevis lattice. Okay, and there are non-brevis lattice. There are non-brevis lattice. Okay. Brevis lattice, okay, they have two properties. Okay, if you go to any point, any lattice point, the lattice should look like the same. So, for example, I told you if I have a say rectangular lattice, okay, if I have a rectangular lattice, okay, say these are the primitive vectors are a2, okay. So I told you the property of brevis lattice is that if you go to any point, okay, the environment should be same. It should look like the same from any point, okay. And the second property is that the position vector of any atom can be written in terms of primitive lattice vectors. Okay, suppose if I want to write the position vector of any atom, I should be able to write and like na1 plus ma2. Okay, this was in the two-dimension case. Similarly, if there are three dimensions, okay, I can write the position as nmlla2, okay, or ka2, whatever you want to write. Okay, so these are the two properties of brevis lattice. And I told you what is non-brevis lattice. Non-brevis lattice is lattice where you have the basis composed of more than one atom. Okay, if there are two atoms, okay, then that is not a brevis lattice, that is a non-brevis lattice. However, we can combine these two atoms, okay, and we can make this lattice as a your brevis lattice. So this thing we have discussed yesterday, and we also discussed about a unit cell. Unit cell is the fundamental building block of a crystal, which when repeats itself its dimensions in all direction, it can recreate the crystals. Okay, and unit cell also, I told you there are two type of unit cell. One is primitive unit cell and there is a non-primitive unit cell. Okay, non-primitive unit cell we also call conventional unit cell. Okay, primitive unit cell क्या होती है? What is primitive unit cell?
Smallest volume and one atom.
Okay, this is a smallest volume.
Number of atoms is one.
One. Okay, per lattice.
One atom.
Okay, very good. This is your
one atom.
Okay, that was your primitive.
सर टोटल शेयरिंग वन होती है ना
हाँ?
सर प्रिमिटिव में टोटल जो एटम्स की शेयरिंग होती है वो सम वन के इक्वल होता है ना?
मतलब शेयरिंग उसका जो सारे एटम्स का आता है वन आता है.
हाँ वही सर, टोटल नंबर ऑफ लैटिस पॉइंट
lattice point is 1. Okay, so now we'll discuss lattice. Now we told the lattice is a infinite arrangement of the project arrangement of points. Okay, and these points cannot be these points cannot be arranged in infinite way. Okay, so in 2D there are only 5 brevis lattice. Okay, so 2D. Okay, brevis lattices in 2D. Okay, so there are only 5 different way we can arrange in 2D. We can arrange the arrange this lattice point. Okay, so and that 5 brevis lattices can again be classified in 4 crystal systems. Okay, so the number 1 is oblique. Number 1 is oblique. Okay, so we have atoms. Okay, okay, so we can arrange in oblique manner. So this is my oblique lattice. Okay, you can draw in parallel way. Okay, so say this is my A1, and this is my A2, this is my primitive lattice vector, and this is the angle between the two. So in general, A1 is not equal to A2. Okay, A1 is not equal to A2, and your phi is also not equal to 90. Okay, so this is your oblique lattice. Okay, and the class system, okay, the crystal system is monoclinic. Okay, so monoclinic. Similarly, the second Brevis lattice is your rectangular lattice, which I have drawn a couple of times. Okay, so you have, this is your rectangular lattice. This is your rectangular lattice. So here, this is your A1, this is your A2. Okay, and the angle is 90. So I can write A1 is not equal to A2 because it's, the magnitude of A1 is not equal to A2. Okay, the magnitude of A1 is not equal to A2, but phi is 90 degree. Okay, so here this is the magnitude of vector. Okay, magnitude of vector. This is your rectangular lattice. Okay, rectangular lattice. Okay, and the crystal system for this one is orthorhombic. So these are the two ways. Now third one is centered rectangular lattice, which also I have drawn yesterday. So I am erasing this one. Okay, so the third one is your centered rectangular lattice, which also falls in orthorhombic class system. So centered rectangular, okay, lattice. Okay, so which falls under again in orthorhombic crystal system in 2D. This is your orthorhombic. Okay, so in this system, okay, we have one more atom in the center. Okay, so we have one more atom in the center. This is your 2D. Okay, third, and the fourth one is your hexagonal lattice. Okay, the fourth is your hexagonal lattice. Hexagonal lattice. Crystal system is again hexagonal. Okay, that means I can draw a hexagonal. Okay, so I can draw a hexagonal. We have here, okay, hexagonal. Okay, yeah, hexagonal. So here the angle is, this angle is 120, and A1 and the magnitude of A1 and A2 is same. Okay, so the magnitude of here again your A1 is not equal to A2. Okay, but phi is your 90. Okay, so here you have A1 equal to A2 and angle is phi
सर
is 120. हाँ,
रेक्टेंगुलर में सर
रेक्टेंगुलर में इक्वल नहीं होते ना, इक्वल नहीं होता, रेक्टेंगुलर में इक्वल नहीं होता. Okay, this is your centered rectangular, this one, so this is A1, this is your A2, and the last one is square lattice. So you can draw a square lattice. Okay, just give me.
सर एक मिनट.
हाँ, I'm searching raster. I can erase this one, na?
Yes, sir.
Yes.
This one I can erase, na? Now we have this your square lattice. This is your square lattice. So in square lattice, you have equal distance points are separated by equal distance. Okay. This is your so this is your A1, A2, and this angle is 90. So your A1 is equal to A2, and your phi is also 90 degree. Okay. So this is your fifth one, and this falls under tetragonal class system. Tetragonal class system. Okay. So these are the 5 unique way of arranging your lattice point. Okay, any other arrangement can be derived by this 5 type of Brevis lattices in 2D. Okay, so this is was your Brevis lattice in 2D. Now let
Sir,
me
सर ये हेक्सागोनल ब्रेविस लैटिस कैसे हो रहा है? साइड तो सॉरी सराउंडिंग तो इक्वल नहीं है.
कैसे
ग्राफिन के जैसे हो गया हेक्सागोनल.
नहीं ऐसा नहीं है एक्चुअली. ओके, so graphene also I told you, there's 2 atoms. If you combine 2 atoms together, okay, then that can be considered your this one lattice. Okay, but इसमें कैसा होगा? Just let me discuss. इसमें कैसे convert होगा? Okay, surrounding. तो अभी मैंने पूरा इसको draw नहीं किया ना. Okay, okay, तो इसमें so you have to create a unit cell in such a way. Okay, so that's a good question. Okay. Okay, let me reply this tomorrow. Okay, because I didn't draw properly this one. Okay, I will tell you tomorrow about this one. How can we create this hexagonal lattice in 2D? Okay, so now just let me go to the 3D part. So in 3D we have a 7 crystal systems. In 3D we have a 7 crystal systems. कौन से systems हैं? Okay, I remember this by calling CTOR, HMT. Okay, so C4, the first C4 cubic. Okay, 2 is tetragonal. Okay, third is orthorhombic. Okay, then
Hexagonal.
rhombohedral or trigonal, na? We got rhombohedral rhombohedral. Okay, we call this trigonal also, and then we have hexagonal. दिख रहा है नीचे hexagonal.
Yes, sir.
And the sixth we have
monoclinic.
And the 7th is your triclinic. Okay. Now I told you we have in the last class in 3D we have 4 type of unit cells. Okay, we have 4 type of unit cells. One. So this is the primitive unit cell. Okay, this is a primitive unit cell. We call it we represent by P. Okay, then we have base centered. Sorry, we have one atom in body centered body. Okay, so we have one atom in body centered. Okay, so we call it BCC, or we represent it by I. Okay, body centered cubic lattice. Okay, the third one we have
CC. सर आपकी आवाज नहीं आ रही. Hello. Hello.
Sir, your audio is paused. Hello, sir.
कोई कॉल कर इन्फॉर्म दो। हेलो
सर आवाज में आ रही।
सर कॉल भी नहीं उठा रहे। बोल दिया सर, बोल दिया।
Okay. Am I audible now?
Yes.
यस सर।
Yes sir.
Okay. So the last one is we call it we replace by S or B. इसमें क्या होता है कि अपोजिट फेस पे ये एटम। हाँ बोलिए।
तो स्टार्टिंग से बताइए, आपकी आवाज नहीं आ रही थी।
शुरू से नहीं आ रही
वो
थी।
सर ये
FCC
यूनिट
वाले
वाला
से
पार्ट।
सिंपल।
FCC. Okay, so we have 7 crystal systems. Okay, and in 7 crystal system we have 4 different type of unit cells. Okay, so this is the primitive, this is the body centered, this is FCC, and this is the base centered. Okay, base centered, or you sometimes we call it by S also, we represent by S also. इसमें क्या होता है कि opposite face पे एक atom होता है। Clear? Now if I combine these 7 crystal systems with these 4 unit cells, okay,
हाँ सर।
then how many? हाँ बोलिए।
सर वो बेस सेंटर्ड का स्ट्रक्चर एक बार फिर से बता दीजिएगा।
मैं
बस केवल 2 जगहों पे।
इसको ड्रॉ कर देता हूँ।
यस सर।
ऊपर ड्रॉ कर देता हूँ। दिस इज बेस सेंटर। ओके, इसमें अपोजिट फेस पे होगा। ओके, so this is X, this is Y, so this is Z. Okay, so sometimes we call it C by C. Okay, if it is an X, we call it A. If it is in X direction, if it B, okay, the Y direction. Okay, or if it is C. Okay,
Yes, sir.
so the general notation is S. General notation is, some books say it is a base centered. Okay, जहाँ पे भी एटम उसको बेस मान लेते हैं. So sometimes we represent by AS, B or ABC. So the only we have atoms on opposite face, not like FCC where we have atoms in each face. Okay, now the question is, now we have total 7 crystal system and 4 unit cell. Okay, if each system accommodates these 4 brevis lattices, then total brevis lattice should be how many? 28, huh? Then there should be 28. But in actual the reality we have only 14 brevis lattices. Okay, there are only 14 way in 3 dimension we can arrange the lattice points. Okay, why it is so? Okay, so let me discuss.
सिमेट्रीज की वजह से।
So let me discuss. So let me discuss for what is first cubic. Okay, cubic you have A equal to B equal to C, or so let me draw a unit cell. Okay, so say इसको रब कर दूं क्या मैं इसको अभी?
यस सर।
we draw again. Okay, so suppose we have a crystal system. Okay, I'm not making symmetric. Okay, so we have a crystal system. Say this is my X. Okay, say this is my Y. Say this is my Z. Okay, so I can say जहाँ पर X है, X के सामने का एंगल क्या होगा? अल्फा. If you Y, the angle in front of Y is beta. If you Z, the angle in front of Z is your gamma. Okay, now if say the X direction, this is a lattice vector, lattice distance A. So they say this is your B, and say this is your C. So in cubic crystal we have A equal to B equal to C, and we have alpha equal to beta equal to gamma is 90 degree. Okay, isn't it? Similarly, if I want to write your tetragonal system, okay, tetragonal system में क्या होता है?
A equal to B, not equal to C.
A equal to B, not equal to C,
Not equal to
and
C.
alpha beta
90 degree.
90 degree. Very good. Okay. In orthorhombic, A not equal to B, not equal to C. Okay. And alpha beta
90 degree.
gamma 90 degree. Okay. So this is your orthorhombic. Similarly, if I want to write this for your trigonal, trigonal में क्या होगा?
A equal to B equal to C.
Equal to B equal to C and
Alpha beta gamma not equal to 90.
Okay, alpha beta gamma, they are not equal and they are not equal to 90. In fact, they are less than 120. Okay. And in hexagonal, we have A equal to B. Okay. Not equal to C. And और क्या होता है hexagonal में?
एक एंगल 120 का होता है.
Okay. So you have alpha beta 90, gamma is your 120. Okay. Then the last is monoclinic. Okay. Monoclinic में क्या होगा? You have monoclinic. Monoclinic में you have A equal A, not equal to B, not equal to C.
Not equal to C.
Okay. Then alpha
gamma 90.
Alpha equal to gamma equal to 90 and beta not equal to 90. Okay. This is your monoclinic. And triclinic में क्या होता है? Triclinic में A not equal to B, not equal to C, and alpha beta
not equal to beta, not equal to gamma, equal to not equal to
90. Okay. So these are 7 crystal system. Okay. And if you see the unit cell, okay, if you see in cubic we have only 3 type of unit cells. Okay. Which one? PIF. We have only PIF. Okay. The base center or S lattice we don't have in this cubic. Okay. Similarly, if I say tetragonal, okay, tetragonal I have only P and I. Okay. Orthorhombic I have all 4 PIF, okay, and S. I have all the 4 type of Brevis lattices. In trigonal में क्या होता है? Only we have only P and I. We have only P and I. Count करते हैं ना? 1 2 3 4 5 6 7 8 9 10 11. Okay. And hexagonal we have only primitive. Okay. Hexagonal we have only primitive. Similarly in okay, trigonal also.
ट्राइगोनल में एक ही होती है.
Trigonal में भी एक होता है. We have trigonal also we have only one. Okay. Trigonal में we have only one. Okay. And then in monoclinic we have P and S. We have P and S. Okay. And in triclinic we have only P. So you can count कितना हो गया? So 1 2 3 4 5 6 7 8 9 10 11 12 13 14. Okay. So there we have total 14 Brevis lattices. Okay. So in 3D we have a total for 14 Brevis lattices in 3D. 28 नहीं है. 28 नहीं है, only 14 है. So I was discussing why it is so. For example, let me show you some okay. Am I audible now?
Yes, sir.
So can you see this PPT? Okay. So
Yes,
I
sir.
told you in cubic system, okay, we have only primitive, body centered and face centered. We don't have a base centered. Okay. So base centered क्यों नहीं है? अगर हम primitive lattice में इसमें cubic system में if you try to make this base one, okay, so you can see this base I can derive the same cubic base lattice by a orthorhombic primitive cells. Okay, because if you see this middle atom, okay, this middle atom, and we combine this, so we can make a tetragonal, we can make it
Sir,
tetragonal lattice. Okay, where A,
Sir?
हाँ बोलिए.
सर आप किस पार्ट से एक्सटेंड करें वो डिस्प्ले नहीं हो रहा, सिर्फ फ्रंट पेज ही डिस्प्ले हुआ हुआ है शेयर स्क्रीन पर.
अभी ये नहीं दिख रहा है, अभी ये lattice reduction नहीं दिख रहा, lattice reduction.
नो सर.
No, sir.
Let me share again. अभी क्या दिख रहा है?
Front
सर
page.
फ्रंट पेज.
ओके, किस तरह से? ओके, अच्छा अभी ये दिख रहा है क्या lattice reduction?
No, sir.
lattice reduction. अभी चेंज भी नहीं हो रहा है.
नहीं
PPT
No, sir.
नो सर.
हाँ सर, आप
अभी चेंज हुआ.
चेंज हुआ ना? अभी क्या दिख रहा है?
Atomic packing fraction.
अभी lattice reduction दिख रहा है? lattice reduction
नहीं सर.
अभी चेंज हो रहा है, फिर अभी नहीं, ऐसा ये क्या लिख रहा है? अभी क्या दिख रहा है?
सर एटॉमिक
Atomic
पैकिंग
packing fraction.
और इसके ऊपर ये क्या दिख रहा है?
वही दिख
तो
रहा है.
बस वही दिख रहा है.
ये lattice reduction नहीं दिख रहा, lattice reduction.
नो सर,
No, sir.
चेंज स्क्रीन पे.
किसने स्ट्रक्चर?
नहीं सर,
No, sir.
एटॉमिक ब्रेकिंग फ्रैक्शन ही दिख रहा है.
ये कैसे? मुझे तो एक दिख रहा, बाकी नहीं दिख रहा है. Just give me 1 minute. अभी मेरा डेस्कटॉप दिख रहा है?
हाँ sir.
यस सर.
Yes, sir.
अभी ये PPT दिख रहा है?
Yes, sir.
टेबल दिख रही है.
हाँ, ओके, जस्ट अभी चेंज हो रहा है?
Yes, sir.
यस सर.
Now this is a lattice reduction. Okay, so
Yes, sir.
I was discussing why we do not have this base centered unit cell in your cubic lattice. Okay, so if I try to make this base centered cubic lattice, okay, so you can see we can combine these atoms, okay, and we can create another smaller one, tetragonal lattice. Okay, so this become now, so this same lattice, okay, this base centered cubic lattice can be derived from your tetragonal lattice. Okay, this tetragonal lattice we can derive, and this is already available. So why to create another one? So this your base centered cubic lattice, this is not a new type of arrangement, because it can again be derived from your primitive tetragonal lattice. Okay, so similarly, if you see this face centered unit cell does not exist in tetragonal system. Okay, because this can be created. Okay, this can be this face centered in tetragonal can be created by a body centered this lattice. Okay, so in this way we don't have a 28 this unit cell. Okay, instead of having 28 we have only 14 Brevis lattices. Okay, the point is clear what I'm trying to say?
Yes, sir.
So I'm telling this base centered, okay, cubic lattice is not a new type of arrangement. This whole arrangement of lattice points, all this Brevis lattice can be regenerated by your tetragonal lattice. Okay, primitive tetragonal lattice. This is not new lattice. Okay, that's why there are not 28 lattices. There are only 14 lattices. Okay, because some of them can be derived by other lattices. Okay, so this was your lattice reduction. And today I am also going to discuss your atomic packing. Okay, so atomic packing means how densely your crystal is packed. Okay, that is derived from your atomic packing fraction. Okay, so for example, if I want to create the calculate the packing fraction of a cubic crystal. Okay, so packing fraction का मतलब है कि कितना dense pack है, कितना volume खाली है और कितना pack है. So for example, this is my primitive simple cubic cell or primitive cubic lattice. Okay, so in primitive cubic lattice I have a atoms in the corner, and these atoms are touching to each other. Okay, these atoms are touching to each other. So if I want to calculate the packing efficiency, I need to first calculate the volume occupied by these atoms and divided by total volume. Now,
So the audio is paused.
Okay. What is paused?
Sir, it is clear.
It's clear. Okay. So now I have this cubic unit cell. I know the volume of this cubic unit cell is a cube. Okay, because this is a cubic cell. So lattice distance is a. Okay, so I can write the volume of unit cell as a cube, and now I need to calculate what is the volume occupied this lattice. Okay, in this unit cell. Okay, so we also know in this cubic lattice. Okay, this the sharing of this corner atom is only 1/8. Okay, so if I try to calculate the effective number of atom present in this unit cell, that is only 1, क्योंकि जो corner का atom है, okay, it is sharing only 1/8, क्योंकि यहाँ पर ये सारा जो ये each atom है, this is shared by other 8 cells. ये पता है ना?
Yes.
ये point clear है कि नहीं है? Okay, so only 1/8 part of this atom is coming inside this unit cell. Okay, so there are 8 atoms, so effectively there is only 1 atom. Okay, so if I want to calculate the volume of atom in primitive cube, only I have one atom. Okay, so I have to write the volume of 1 atom. If I know the radius, I can write this 4/3 pi r cube. Okay, and I can divide by this volume of unit cell, and I can calculate the packing fractions. Okay, so just see here that in cubic lattice all the corner atoms are touching to each other. All the corner atoms are touching to each other, and then we'll calculate this on the board. Okay, so this is my simple cubic crystal. Okay, and then we have this your base centered cubic lattice. Okay, so in this base centered cubic lattice, what is there? My corner atoms are not touching each other. You can see these are not touching each other, but they all are touching to this this center atoms. Okay, which is the center. So these all atoms are touching to center atom. That is why it is called body centered cubic lattice. Okay, similarly, if I show you the FCC, okay, FCC lattice, in FCC lattice all the atoms, okay, they are touching this center atom on the face. They are face centered. Okay, so all atoms they are touching to this face, this mid atom. Okay, so this point is clear. In face center they are touching to center atom face. Okay, body center they are touching to the middle part. Okay, and then simple cubic, the corner atoms are touching to each other. Okay, now I can stop sharing and we can calculate the atomic packing fractions. Okay, so let me come back to again the board. So now I want to calculate atomic packing fraction. Okay, for different type of unit cells. So put the heading now, atomic packing fraction. So, atomic packing fraction. Okay, atomic packing fraction. Okay. So I want to calculate for simple cubic, for primitive cubic lattice, simple cubic. Okay, so I have this simple cubic. Okay, so I have atoms at the corners. Okay, and I told you these all atoms are touching to each other. Okay, so if I want to find out the relation between lattice constant and the radius, I can find out easily because these atoms are touching to each other. Okay, so these are touching to each other. This distance is a, this distance is a. Okay, and I know this is the radius of atom, this is also radius of atom. So that means for simple cubic system I can write my a equals to 2r. Okay, now I want to calculate the atomic so n effective. Okay, the number of atoms present in cubic crystal is simple cubic crystal is 1. So I can write atomic packing fraction APF, volume of atom. So there's only one atom. Okay, and their volume will be, they are spherical, we are using spherical, so there will be 4 pi r cube, and the volume of unit cell is a cube. Okay, so I can now calculate the packing efficiency. So packing efficiency क्या आ जाएगी? A equal to 2r है, so you can write 1 into 4 by 3 into r cube, and you can write here 8 a equal to 2r, so you can write 8 r cube. Okay, r cube cancel, so you will get what? 4 upon कितना आएगा?
pi by 6.
Pi by
5 by 6.
4 pi by 6. Okay, and
नहीं
so
सर, 5 by 6. 5 by
So pi by 6 है वो.
5 by 6.
4 2 8
5 by 6 तो है, ये 4 आ जाएगा,
नहीं आएगा
2. Okay, और 2 pi by 6 only. Okay, pi by 6. Okay, pi by 6. So pi by 6 को सॉल्व करो कितना आएगा? It should come around 0.52.
52%. Yes sir.
So that means this is a 52%. Okay, so the packing frequency for simple cubic is 52%. That means आपका 48% जो place है वो vacant है. Okay, so void space is, okay, void space is 48. Okay, void space, खाली empty space. Void space is your 1 minus 0.52, that is equal to 0.48, or in percentage you can write 48%. Okay, this is for simple cubic. Okay, now similarly we can calculate this for our other systems also, BCC also. Okay, so calculate for BCC now. Calculate for BCC. BCC के लिए कैसे कैलकुलेट करेंगे? So in the case of इसको can I erase this one ना? ये तो कर लोगे ना?
Yes.
Yes sir.
Okay, so I can erase this one. Okay, so in the case of BCC, okay, we have one atom in the center. Okay, so we have one atom in the center. Okay, so that means now if I want to show, okay, थोड़ा ऊपर बढ़ाने दो. If I want to calculate the relation between A and R, atomic radius and lattice constant, so I can calculate the relation. Okay, so we have atoms here, we have atom in the corner. Okay, and I told you so all atoms are, I'm taking body diagonal. Okay, so I have these atoms. Okay, I have these atoms, I have this atom. Okay, and I have one atom touching to these things. Okay, so this is my R. Okay, this is 2R, this is 2R, and again this distance is R. Okay, so this total distance is 4R. Okay, and if I want to take this distance is A, and okay, this distance is A, and this distance, okay, A, this distance is root A. So if I want to find the relation between this one, so we have these 3 atoms. Okay, we have this R. Okay, 2R, R. Okay, total we have 4R. Okay, and then we have, okay, 4R, and then we have this distance A. Okay, and this distance, okay, this distance is your root A. ये perpendicular है ना तीनों ही. Okay, so I can write now my 4R. Okay, 4R square is equal to root 2A का square plus A square. That means 16R square is equal to 2A square 3A square. Okay, so my R will be what? My R will be root 3A under root of 2, that is 4. Okay, so this is the relation between R and A for my body centered. आप लोग को ये आ रहा है कि नहीं आ रहा है?
Yes, sir.
Yes sir.
Yes sir.
तो बैकिंग फ्रीक्वेंसी निकाल लो। Okay. So now you can calculate the atomic packing fraction. Okay, कितना आएगा? So I want to calculate that atomic packing fraction. Okay, so atomic packing fraction is what? Now this is the BCC. N effective कितना है इसमें? 2. Okay, N effective is 2. 8 atoms कोने के, that will contribute 1 by 8. Total is 8 atoms. So 1 एक बीच में. Okay, so we have now 2 atoms. So 2 into 4 by 3 pi r cube. Okay, and we have volume of unit cell A cube. So this becomes 8 by 3 pi. Now r I can write. Okay, A cube. Okay, in terms of this one, so r cube क्या हो जाएगा? √3 a cube A cube. Okay, into 64. Okay, 64, and then we have A cube also. So this will cut this one. Okay, so 3 will cut. So I 3 will cut. I will be having only √3 here. Okay, and this will cut here 1 here. I will be having 8 only. So I will be having packing APF equal to how much? Pi √3 by 8. Okay, और you solve this one कितना आ रहा है?
68%.
So if you solve this one, this will come 0.68. Okay, or 68%. Okay, so it's a better one, better than your simple cubic.
सर आपने NEFF का डेफिनेशन क्या बताया, प्लीज फिर से रिपीट
एंड एनी इफेक्टिव मतलब कितने इस यूनिट सेल में कितने इफेक्टिव एटम्स हैं, कितने इफेक्टिव एटम्स हैं, इसका मतलब यू हैव दिस योर बॉडी सेंटर्ड. ओके, तो बॉडी सेंटर में क्या है, आपके 8 एटम तो कॉर्नर में है. ओके, तो ये जो एटम है इस सेल में ओनली 1/8, इसका कंट्रीब्यूशन ओनली 1/8 है, क्योंकि इसके आसपास 8 सेल और है ना, 7 सेल और है. ये एटम क्या है, एक इसके ऊपर एक सेल है. ओके, एक इधर सेल है, एक इधर सेल है, ऐसे करके कुल मिला के 8 सेल है. पीछे की तरफ 3 सेल है. ओके, सो इफ यू मेक दिस क्यूबिक लैटिस complete, then what will have, you will have this atom contribution in this unit cell only 1/8. Okay, so n effective क्या हो जाएगा, n effective we have 8 atom which are contributing only 1/8, और एक सेंटर में है. सेंटर में वो तो किसी के साथ शेयर है नहीं ना, वो तो इसी यूनिट सेल के अंदर है. तो हमारे पास एक 1 है, तो क्या हो जाएगा, 1 + 1 कितना हो जाएगा, 2 एटम्स n effective.
ओके
क्लियर है?
यस सर.
Now calculate for FCC. Calculate for FCC. Okay. Now in the case of FCC, we have atoms on the face. Okay, we have atom on the face. 6 face है, एक पीछे है, ये आगे. ओके, सो ईच फेस वी हैव ओके 1 एटम, एंड n इफेक्टिव क्या हो जाएगा, कॉर्नर पे 8 एटम है, सो 8 × 1/8, और जो फेस पे होता है इसका कंट्रीब्यूशन हाफ होता है, क्योंकि इसके ऊपर खाली एक और रख सकते हैं. तो ये इस यूनिट सेल का, और इसके ऊपर यूनिट सेल उसका पार्ट होगा. सो इसका जो फेस पे जो होता है उसका कंट्रीब्यूशन क्या आता है, हाफ. सो हाफ, और हमारे पास 6 एटम्स हैं, 6 एटम्स. Total become 1 + 3. We have 4, and effective is 4 in the case of your FCC lattice. Okay, and I told you in the FCC lattice, your voice is not clear, कट रहा है तुम्हारा, ब्रेक हो रहा है.
सर ये 1/2 वाला कॉन्सेप्ट,
1/2
1/2 वाला कॉन्सेप्ट.
1/2 आपके जो फेस पे जो एटम होता है, इस सर फेस पे यहाँ पे 6 फेसेस है ना, तो 6 एटम आ गए, और ईच फेस एटम ओनली कंट्रीब्यूट्स हाफ 50% इन 1 यूनिट सेल. क्योंकि क्या करोगे भी, आपके ऊपर ये एक क्यूब है, इस पे एक एटम है, इसको रख दिया, ओके, तो क्या होगा, आपका कंट्रीब्यूशन तो आपका हाफ ही आएगा ना। तो फेस है, जो फेस होता है, अब ये यहाँ का भी एटम है और इसकी आगे वाली का भी, आगे ऊपर जो यूनिट सेल है उसका भी एटम है, तो यहाँ एक ही एटम है, एक ही एटम दोनों फेस के भी शेयर हो रहा है, तो ये इस यूनिट सेल का पार्ट भी है, इसके टॉप में जो यूनिट सेल है उसका भी पार्ट है। सो दिस इज कंट्रीब्यूटिंग ओनली हाफ। तो मेरे पास 6 फेसेस हैं, टोटल हो जाएंगे 3 एटम्स, एंड इफेक्टिव इज 4। ओके, now you can calculate the relation between A and R. Okay, so we have these atoms are touching to face atom in, ये क्या है मैंने बताया ना, डायग्राम बताया था, where these atoms are touching to only this middle atom. Okay, जो surface पे जो middle है, only they are touching there. Okay, so this is my atom, this is my lattice distance A, this is my lattice constant A. Okay, so and similarly this is also A. Okay, this is also A, and if you want to calculate this one, this is R, so this is my 4R, R. Okay, R, 2R, and this R, 4R, and this is my AA. Okay, so I can write my 4R. Okay, 2R square or 4R square is equal to A square plus A square. Okay, so I'll get 16R square equal to 2A square. Okay, and that will give me R square equal to A square by 8, and R will be what, under root 8, so A by under root 8, that means 2 root 2. So this is the relation between R and A. Okay, now I can calculate what, now I can calculate your packing efficiency. Atomic packing frequency is, there are four effective atoms, and 4/3 pi R cube, okay, upon A cube. So this will give me 16/3. Okay, 16/3 pi R cube, I can write A cube. Okay, 2 की जगह 8, and cube 4 into root 2, A cube cancel, so this will give me 4. Okay, this will give me 2, so I have 1/6 root 2. ये आ रहा है क्या?
pi by 3 root 2.
pi by 3 root 2.
pi by 3 root 2. Okay, 3, sorry, 3 pi by 3 root 2. तो 2 कहाँ से कटा, 2 कहाँ पे कटा, ये 16 था, so 8 2 और 2 यहाँ से कटा. ओके, तो यहाँ का 2 कहाँ गया फिर वो, कितना आ रहा है तुम्हारा आंसर, कितना निकालने में कितना आ रहा है
सर? pi by
0.74. So 0.74.
0.7.
ओके, सो R क्यूब ना, R क्यूब A क्यूब ऑफ दिस वन, इसका क्यूब करेंगे कितना आएगा 8, इसका करेंगे, अच्छा इसका 2 root 2 आएगा, सही है 2 root 2 आएगा, इसका कम 2 root 2. नाउ इट्स ओके, सो आई विल हैविंग नाउ pi by 3 root 2. So 0.74 आ रहा है, 72 आ रहा है,
7.4 sir.
74. Okay, 0.74. So this is the for 74%. Okay, now tomorrow we'll calculate for hexagonal or other type of crystals also. Okay, SCP and NaCl और भी जो है उनके लिए हम लोग will calculate this atomic packing fractions. Okay, so I'm stopping here.
Yes, sir.
Okay.
Sir,
हाँ बोलिए.
sir, one request. Can you
हाँ.
please share that presentation in the group?
हाँ, वो प्रेजेंटेशन में शेयर कर दूंगा, उसमें थोड़ी मिस्टेक्स है, उसको करेक्ट करके मैं शेयर कर दूंगा. ठीक है, अभी उसमें से पढ़ाना भी है, पढ़ा के मैं शेयर कर दूंगा.
Thank you, sir.
ओके,
Thank you sir.
Thank you, sir.
Thank you, sir.
Thank you very much.